Second section of this unit is going to be our discussion of the Enlightenment. And we'll get into what this intellectual and philosophical movement was. This is going to cover roughly the 1550s to 1800s. We'll move past that or cover a couple different things, but that's roughly what we're talking about. We're going to split this up into two videos. The first video on the Enlightenment is going to cover the scientific revolution, and our second video that we'll get into next is going to get into philosophy that's going to be developed during this time period. So when we're talking about the Enlightenment, the monarchs of Europe have issued their orders and they want to work forward. And so that's what we've seen as we moved out of the medieval world into the Renaissance and the Reformation. The question is, are we really actually moving forward? And we talk about this idea of progress with the capital P or progress with little p. But as the monarchs are kind of pushing forward and advancing their own agendas, the intellectual world is going to move and follow. So as we talked about with the Renaissance, we're really in Western Europe, moving from a world based on one of the church and on faith. You're accepting what the church is telling you about the universe at face value, which is again the medieval worldview, which is one that's grounded in trust. I'm trusting the priest is saying the right words at the right times during Mass to absolve my sins to be able to go into the eternal kingdom of heaven. Right? I'm trusting that what the church is saying about the universe and the math they've done is correct. To a more modern worldview, right, was one where the state is the kind of ultimate player, and your own and other people's own reason is what's driving the world forward. This is a much more modern worldview, which is going to again be grounded in proof. How can you prove what you're saying? How can you prove to me what you're doing? I'm not just going to accept on face value what you're saying. You have to prove it. I need empirical, solid data to be able to understand how you reached your conclusions, and does your mathematics, does your physics, does your experiments back up that data? So what we see here is the scientific revolution and the Enlightenment is a triumph of reason, and it's going to create a whole new worldview about how Europeans and how Western Europeans are going and visualizing how the world is composed and how the world works and how we work within this world itself. So if you're again, some of the kids are usually taking geometry at this point. So if you've taken geometry, you've talked about proofs. That side, how can you prove that this angle is equal to that angle and side equals side and all that stuff. So and a proof that we can think about with the Enlightenment is that to be able to explain things, you need to acquire knowledge. So in order to be able to explain about the Enlightenment, Mr. Cranmer had to go acquire knowledge about the Enlightenment to do that. But the question then becomes if you're trying to explain why the sky is blue and why grass is green and why dogs know how to sit but zebras can't, right? The question becomes where are you acquiring that knowledge from? Where do I get this? So then to acquire knowledge, the Enlightenment movement says you need to free your mind to be able to go and say, well, zebras can sit because they've got a butt, they've got hind legs, they can just go do it. But can they sit? Are you thinking about it? Are you Googling that right now? Right? So you need to be able to free your mind from what? What do I need to free my mind to be able to understand something that isn't there? And to be able to free my mind from preconceived notions of what I've seen in the Madagascar movies with the zebras or in at circuses or at zoos. I need to be able to free my mind, get rid of any preconceived notions that I have about zebras or why the sky is blue or why it snows when it does and what's snow made of and are we all individual snowflakes? Am I blowing my mind? You need to be able to turn to reason. And the Enlightenment very much is saying that there is a reason for why things happen in the universe. And if you can use your reason, if you can apply that reason to the natural laws that govern how the universe works, you can be able to explain things and be able to understand how we fit into the larger universe. This is the idea of using your reason, which is going to equal knowledge, which is going to equal progress. Yay, this is great and awesome. But the question very much becomes for whom? And this is an idea that we'll start talking about as we move towards the end of the semester here, is we talked about how great things are today and how wonderful things are and how I can go to Amazon and get 30 different types of ketchup. and delivered to my house within sometimes a couple hours, even a couple days. We can drive in cars that can go hundreds of miles an hour that have sound dampening, so I can listen to my tunes while I'm cruising with the sunroof open and the wind in my hair, blowing it all over. Right? We can have the internet with all the known information of the universe at our access delivered to us at the speed of light, the speed limit of the university. That's all great, but we also have um, atomic bombs and thermonuclear devices and machine guns that can fire 6 bullets a second. So it very much becomes this idea of we're advancing there, but some of these advancements are good for mankind, but others are, who's to say? So that's something to think about as we continue to move through through history and towards the 20th century in our own present time. The scientific revolution, again, is very much, are we going to accept the world based on faith, or are we going to accept a world based on reason? Or are we going to accept a world that deals with what the church is saying about how the world works and the universe is created and we're related in nature, or are we going to rely on science? And so what we see in the Enlightenment is a discarding of truth based on tradition. This is the way things always have been done, so this is why we're going to do that. I'm recording this 2 days before Thanksgiving here in 2023, and so we all have our Thanksgiving traditions where we do this at this time, and we do this at this time, and we go to this place, or we have this meal, or and so we have these traditions that kind of govern our lives, and this is why we do that. But the question might be why? Why do we do these things when we do that? It might not just be why we have our grandma's sweet potato casserole on Thanksgiving, but it might be a grander things of why do we have uh, miles per hour instead of kilometers per hour? Right? Why do we go and measure temperature the way we do? And why do we have things and trying to find that truth that way? And so, what the scientific revolution is this search for truth, and it's a search for truth, and this is the key kind of idea that makes the scientific revolution happen, is a search of investigation through evidence. It's not just accepting what other people have done, it's double checking their math. It's understanding what they've said, why they've said it, and what they're trying to prove. When we're talking about the scientific revolution, we want to first understand when we put on our science wear, the medieval view in the Western Europe during the Middle Ages is very much that why should we go against one, what God is saying in the Bible, and two, why should we question what Galen, Hippocrates, Aristotle, Plato, Socrates are saying? If all of their stuff seemingly makes sense, why should we go and double check them? Or why should we go and do anything differently? Because they're right. So we're just going to rely on those ancient sources and the Bible. And what we see throughout the Middle Ages is very few scholars are willing to make observations themselves because they're saying we've already got this bulk of evidence. It very much seems to be the case. If we want to get in the weeds a little bit, there's a little slight religious coloring to it as well. But it just makes sense. So we're just going to go with the flow and accept everything that it has. So a great example of this is what's called geocentric theory. Geo meaning earth, centric meaning center. So an earth-centered view of the universe. And so this becomes very much the worldview of Western Europeans, is this idea that Earth is at the center of the universe and everything goes and revolves around it. This makes sense, right? Stand outside on a summer day and what do you see? You see the sun move across the sky. Seemingly you're not moving, it's the sun that's moving, right? You're so excited about learning all about the sun that you go and you stay out there and you watch the moon. And the moon goes and moves through the night sky. The stars move through the night sky. You're seeing all this and you're still stationary. You're on the earth. To your point of view, it looks like everything was revolving around you. So Aristotle and Ptolemy in the early centuries BC came up, proposed this idea, and it very much became the accepted worldview. Christianity works to confirm this worldview as well. If you go and you read the story of Exodus, right? Moses goes before Pharaoh, all right, points his staff at the sky and says, "Let my people go, or God will stop the heavens." And he points it there, and God stops the sun from moving. So if you follow that line of logic, then obviously God is saying the sun moves, the earth doesn't. Ipso facto, geocentric view of the universe. So that's the kind of stuff that we see being accepted scientific view from this point forward. So that's kind of the foundational point where the Europeans are working with through the Middle Ages. But as we start to get into the Renaissance and in this period called the Scientific Revolution, we're going to see that this is a shift in how people, particularly of Western Europe, view the world. So the scientific revolution and how we're talking about this is a new way of thinking about the world based on key parts here: careful observation, and even more important, we'll get the laser pointer out, a willingness to question accepted beliefs. We get into this a lot with people where you're coming in a lot of times as freshmen. This is the way things always have done, and this is the way it is. And the question becomes why. Right? We had a couple of years ago pretty thorough and enthusiastic debate when I dare question a particular student on the baseball team, and I said, "What's the job of a pitcher?" And very simply, the job of a pitcher is to get outs. That's their job. So a pitcher should, one, try to throw as few pitches as possible, because you only need one pitch to hit a round ball to throw to the first baseman to get an out. You don't need to throw 100 million miles an hour. You don't need to throw strikes. You need to throw to contact to make your defenders catch the ball. Right? And Mr. Kramer, this is and we had all these different people. It's so simple, right? And so again, you don't need to throw strikes in baseball. You don't need to. It's the point of the game is to get outs. So you want to be able to go and do that, right? And so again, we get the idea of, we see this in the NBA right now. What is the point in the entire point of the NBA? The entire point of the NBA is to score points. You can score more points if you get 3 points per possession. So we see this all the time. I've got a 18-month-old daughter. If I want her to play basketball, what am I going to do? I'm going to line her up behind the 3-point line and just have her chuck threes the entire time, right? So she gets good at that, with the idea being that I can get more points per possession if you go down against me and my daughter, right? And your team gets 2 points every time, but we get 3 points every time. Simple mathematics is there, right? So this gets in the idea of, should you play defense, right? Do you have to play defense if in basketball, in football, in soccer? The point is to score goals. My team can still win a game. If I score 10 goals and your team scores 9 goals, I win the game. What is the point? To win the game. So this is where we start getting things, people are not willing to question this accepted belief. And I'm going to blow baseball players' minds every year when I say throw strikes. You don't have to. You get outs. And Mr. Kramer is no. What's the point? All you gotta do is just make it so that you throw strikes, throw sinkers, and bing, bada, boom, you're a Hall of Fame pitcher. So that's the whole idea. And if you're not willing to question these accepted beliefs, then why bother, right? Stick your head in the sand, go live in a cave on Mars with your hands covering your eyes and your fingers in your ears, right? So this next part here is important. Freshmen screw this up every year on this simple essay question I'm going to ask you is, why now? Why does the scientific revolution happen now? What are the causes of the scientific revolution? So when we're asking this question, see there's a question mark there. When we're asking this question, we're not asking about the thermometers and the barometers and these things. That we're asking, of all the times on the earth, why does the scientific revolution happen at this point in Western European history? So the first reason is that new discoveries begin to open up the possibility that there are even more new truths to be found. If you had no conception of what a pumpkin is, and then all of a sudden I give you a pumpkin, what else is out there, right? If I tell you that there's an animal that has a bill like a duck, but has fur like a beaver, but has flippers, right, like a seal, and has poisonous spikes on its elbow, and uses electricity sensors in its beak, you're going to call me a flat out liar, and you're going to say I'm an idiot. And I'm going to present you with a platypus, right? Because that if something like a platypus exists that lays eggs like a snake and yet is still a mammal, then what else is out there in the universe, right? And so that's going to keep driving, and it's going to pique curiosity of what people have. The printing press goes and helps spread these new ideas. With the printing press, you can go and write about a platypus, print out 1 million copies, and that's then again keep driving, learning, and keep driving things. The more you read, the more you want to learn about more things. It drives on there. Right? It's the old classic. I'm going to go on Wikipedia because I have one question, and then 7 clicks later, I'm now knee deep in Neanderthal sewing techniques because again it drives that curiosity because all that information is now available. And then finally, the wording here makes sense, but make sure you understand what it's saying. Exploration is going to fuel further research. So we're not into fuel research. The more we explore, the more you want to make those journeys quicker, faster, cheaper, more efficient, which is going to drive even more scientific innovations, and it's going to keep going, right? We have Velcro now today because scientists in space needed a way to stick things in zero gravity. So that's going to help drive even further and further result. So these are the reasons and causes why exploration and the printing press and these new discoveries help drive the scientific revolution at this particular moment in time. Is a geocentric view of the universe, very much described by Aristotle and Ptolemy. At the center of the universe is the Earth. And then Aristotle kind of describes it as almost glass concentric spheres that go and surround the Earth, and each on one of these independent moving spheres is the moon, is Mercury, is Venus, is the sun, and is Mars. So if I were to hop on a rocket ship and go blast off and go out from the Earth, to be able to reach Mars, I'd have to in theory, break through these concentric glass lines. Think of like a rushing nesting doll, and that's kind of how Aristotle is describing the universe, and what Ptolemy in Hellenistic Egypt is also going and describing how the universe goes and works. So this is the geocentric view of the universe, as again we're talking about how we're moving from a medieval worldview where Aristotle and Ptolemy say this in the 2nd century BC, and now as we move 1,000 years, 1,500 years after that, how people begin to say, let's check this math and see if it makes sense. So we're going to break this scientific revolution down into a couple different branches of science and mathematics. So the first group of people we're going to talk about are astronomers. Our first astronomer is Nicholas Copernicus. Copernicus is a Polish astronomer, and he, as he begins to make his observations of the night sky, he begins to question this geocentric view of the universe. It says this may not be wrong, and he proposes a heliocentric view of the universe, or heliocentric theory. Heliocentric, helios for sun, centric for center, is a sun-centered universe, that the Earth is actually revolving around the sun, that the sun stays relatively in the same spot. Again, it's orbiting parts of the Milky Way galaxy, which is orbiting parts of the other parts of the universe. But that's what he's going proposing. Now, Copernicus knows the writing on the wall, and this goes and literally contradicts what's in the Bible. So this might not be something to proselytize and shout high and wide, but his observations and his mathematics support this view. So he's going to write a book that explains this, and this book is On the Revolution of Heavenly Bodies, that's published in 1543 after Copernicus dies, because Copernicus does not want to have to deal with the weight and the guilt and all these problems in any of the things that the Catholic Church might want to do if he's going against these previous ideas. So that's going to be published posthumously after his death, but that again is published with the printing press and starts to get these ideas out there. Our next astronomer is Tycho Brahe. He is Danish. He is very much a interesting figure in history. He is a charismatic personality. He gets himself into trouble and out of trouble pretty famously. He gets into an argument with one of his fellow students at university. They have a duel. In that duel, he gets his nose cut off over a math argument and has a artificial nose that some people say is made out of silver. Probably be expensive, maybe lesser extent, probably made out of bronze. But he's going to carry with that for him for the rest of his life. Tycho Brahe is going to work for the King of Denmark, and he's going to spend 30 years eventually on his own private kind of rock star astronomer existence on his own private Danish island in his observatory, recording the night sky. And he does this day in, day out, night in, night out for about 30 years, going and meticulously recording the planets and stars movement on the night skies. And this is a giant amount of data. Now, helping Brahe out is Johannes Kepler. Kepler is German, but he's going to be working with Brahe's numbers. Kepler's asking Brahe to, can I use your data? Can I use your data? And Brahe's got this locked up under lock and key. Now, Brahe is going to die under unusual circumstances. He's going to die from a bladder infection. The story goes he goes to a party and he doesn't want to be rude, so he holds going to the bathroom. He keeps holding and holding and holding until his kidneys rupture, and then he goes and he dies. But if you're Kepler, you really, really want this data. So foul play, an excellent little murder mystery there for you. So using Brahe's data, Kepler goes and looks at it, and he's able to conclude that mathematical laws govern planetary motion. And Kepler's laws of three laws of planetary motion help go and confirm, or at least makes it so that heliocentric theory makes a lot more sense mathematically and helps goes and explains a lot of the observed movements of the night sky. So Johannes Kepler is famous for his three laws of planetary motion. So here's Nicholas Copernicus. And so again, Nicholas Copernicus is describing a heliocentric view of the universe. And so what we'll see here on these two different GIFs is this idea that, again, the Earth is staying relatively similar, but the planets are revolving around them. Now, heliocentric um, uh, heliocentric theory also makes sense if you go and you put through Kepler's three laws of planetary motion. So Kepler's first law is that planets move in elliptical orbits with the sun as its focus. So if you can kind of go and see there from the GIF on the left is that these aren't perfect circles, these are elliptical orbits that are moving that way. Kepler then describes that the planets cover a same area of space in the same amount of time, no matter where it is in the orbit. The idea that equal areas and equal times, meaning that you're actually moving as a planet faster when you're closer to the sun, meaning that the orbits have the sun kind of at one end of the left or right end of the uh, ellipse rather than kind of straight at the center. So you're going to move faster when you're closer to the sun and slower when you're away. And also his third law is a planet's orbital period is proportional to the size of its orbit, its semi-major axis. Basically, it's the inverse square law, so which makes sense. It's a lot of fancy way to say the farther you are away from the sun, the faster, the closer you are to the sun, the faster you move around the sun. The farther away you are from the sun, the slower you move. So Mercury, closest to the sun, takes like 88 of our Earth days to go around the sun, where Saturn takes 10,700. And so that's what Kepler is going and describing in his three laws of planetary motion. So here's Tycho Brahe. So he's going to record the night sky and his data, and then Kepler is then going to use that data pictured here to be able to then go and describe a heliocentric view of the universe. The last of our major astronomers is Galileo Galilei. Now he's Italian, and what he's going to do is, and we're moving forward through time, the Dutch have been making glass lenses to be able to look at small things up close. And Galileo is just basically going to reverse how those microscopes work to build a telescope to make things that are far away seem up close. And so he's actually going to use a telescope to observe the phases of Venus, to observe the moons around Jupiter and Saturn. And taking a look at all these observations, in 1610, he's going to write his book, Starry Messenger, which goes and supports Copernicus and Copernicus' heliocentric view of the universe. Now, the church is not happy about this, and the church says, hey, Galileo, you better be quiet. You don't want to say anything about this, or else we're not going to be happy with you, and we're going to come and we're going to get you. Right? So Galileo says, all right, I don't want to upset the boat too much here. So he goes back and he makes more observations and he goes and does more physics and he keeps going and he writes in 1632 another book, a dialogue concerning the two chief world systems, where basically he says, here's all the evidence and all the reasons why geocentric theory of the universe is correct. And then here's all the evidence and reasons why the heliocentric view of the universe would be correct. And on like the last page, he says, and heliocentric is right, Copernicus is right, Galileo is right, I'm right. So in this book, Galileo is still supporting Copernicus. The church told him, Galileo, do not do this, so they're upset with him. So in 1633, the church brings Galileo to Rome to stand trial, and under the threat of torture, he reads a confession that says, I'm wrong, the church is right, I'm sorry, and I'm going to pretty much can relent to living under a house arrest system as punishment until his death in 1642. Now, probably not true, but and probably apocryphal, but the story goes is that once Galileo, in front of the church judges, in front of the bishops, after he's done reading the confession, he mutters under his breath, but it still moves. It meaning the earth, right, or revolving around there. So again, makes for a good story. Is it true? Hard to know. But then again, if you watch the movie version of this, that's probably what we'll go and we'll see there. So here's Galileo doing Galileo things later in life, holding his telescope there in his right hand. And then again, this is the big point in the movie where the music swells and Galileo has to go make a decision, and he says, yeah, sorry, I'm going to have to go and recant my views, and here's why I'm wrong. Luckily for Galileo, the Catholic Church will eventually admit that they're wrong and offer an apology. However, they won't be apologizing to Galileo into the 1990s. So he gets his apology, but the Catholic Church notoriously for working a little slow. Philosophically, the big thing that happens in the scientific revolution is the kind of formulation of a scientific method. And this comes out of Francis Bacon, who lives in England. This is very much Bacon working his way through inductive or deductive reasoning. Um, Deductive reasoning is kind of going and taking all these pieces of evidence and then working from that, deducing the reason and the cause for that. Inductive reasoning is starting from a something existing and then working all the different causes for there. So Bacon is very much for deductive reasoning, and this is kind of like how Batman or a police detective would solve a crime, or Sherlock Holmes. Go to a crime scene, see all the clues, and see how those clues add up to do that. So what Bacon is advocating for is what eventually you'll be doing in your biology or chemistry or physics classes here at Joliet Catholic, and that's the scientific method. We're going to make an observation about the universe. Here's something that I'm observing. You're going to make an hypothesis, an educated guess for why you think that observation is occurring, and then you're going to devise an experiment to test that hypothesis to be able to see if that's right or wrong. So this gets into Bacon's major idea of empiricism, that you don't jump to conclusion, you experiment. From those results of those experiments, then you draw your conclusions. And he's writing this in his book, The New Organism, or in Latin, The Novum Organum. So here's Francis Bacon. That's the cover page to his book. And again, Francis Bacon, hints, winks, and nudges, a big deal in terms of the scientific method. All right, next group of scientists are going to be working in the realm of mathematics. Now, I would save some space in my study guide under René Descartes, but René Descartes is French. He's going to do a lot of work in mathematics, working with logic and analytical geometry. His work is going to be helpful in writing the logic that runs our computers that allows me to speak into the computer, to have it be recorded, and then have that video be saved, exported, and then uploaded to the YouTubes. So he's going to be a big deal in terms of that, as well as analytical geometry. He's going to apply this logic to philosophy. So we'll see why Rene Descartes is important for philosophy in the Enlightenment in our next video. Isaac Newton is going to be the big guy here in terms of mathematics during the scientific revolution. He's English. Newton studies mathematics and physics at the University of Cambridge, and he's going to be a big deal, really important. You know him. You can kind of see the GIF that's happening over there on the right. So this is important. Newton's going to be important for this discovery of four different things. Number one, he comes up with the idea that the same force that rules all matter on Earth rules the motion of the planets in space. And this force that makes an apple fall from a tree, that goes when Mr. Cranmer throws a baseball, eventually brings that baseball to the ground, is the force of gravity. This also is what keeps the universe moving. It keeps the sun from spinning off into the universe and turning the Earth to a ice cold rock. So first thing he comes up with is gravity. Now I usually like to demonstrate for my classes, is gravity a weak force or a strong force? And we'll give you a second to go and think and kind of try to blues cruise this. You're wrong. Gravity is incredibly weak. Every time you jump, you are breaking the force of gravity until gravity then goes and acts upon you and pulls you back down. Okay, so gravity is incredibly weak force. Right? Think about how electromagnetism and a magnet can pull something up off the ground, breaking gravity. Think about the weak nuclear force or the strong nuclear force that holds your atoms together, that makes me be able to sit down on a chair, that makes my hand be able to rest on a desk, because the matter of my hand is different from the matter of the desk. So gravity, a pretty weak force in comparison to some of the other ones that are out there. Newton comes up with his three laws of motion, which he's pretty famous for. We'll show you some GIFs to help you work your way through that. He invents calculus, which is a major big deal. And he also does a lot of work, the fourth thing, in optics, to be able to describe how light gets into our eyes and how glass and other things shape and be able to magnify or minimize different things. Now, his invention of calculus is probably the biggest thing that he is famous for. So in 1687, he writes his book, The Mathematical Principles of Natural Philosophy. In Latin, it's shortened to the Principia. And this is probably one of the most fundamental books written in terms of mathematics in the history of the world. This is the book that makes the 20th and 21st century possible, because calculus basically describes the inner workings of the universe, from the electrons in the atoms in our cells to the Earth revolving around the sun. So he does all this, again, without satellites, without computers, with just pen and paper. So Isaac Newton, again, a real big deal in terms of mathematics. This is him describing optics and calculus in there. And then remember, he's also famous for his three laws of motion. So the first law in the up in the top here is the law of inertia. An object in motion stays in motion. An object at rest stays at rest until an outside force acts on it. If you're in a car, if you're inside the car and the car's traveling 60 miles an hour, you're traveling at 60 miles an hour. So if you have a baseball and you hold it outside the window of a car and you drop that baseball, you just drop it, you just let go, that baseball is traveling at 60 miles an hour. Right? So when you have an object that then outside force that acts on it, right, and you're not seat belted, this is why this guy is then spinning out of there, because when the car stops, his momentum, his inertia is still carrying him with that force. He goes over the wall or through the windshield there. Right? So this is why having like tissue boxes in the back of your car is a bad idea, because if you get into a car accident and you go from 60 to 0 miles an hour, that tissue box is now a tissue box with four sharp corners hurtling at the back of your head at 60 miles an hour. His second law is mathematical equation, force equals mass times acceleration, F equals ma, to be able to describe how forces works in math and acceleration. And then finally, the third idea is that, again, for every action, there's an equal and opposite reaction. So when this explosion pushes the ball out of this cannon, the explosion is also exerting a force on the back of the cannon. I like to describe. I like to shoot clay pigeons with with shotgun shooting, and I like to shoot a rifle for target practice. Um, I can't just go and shoot my shotgun or my rifle for hours and hours and hours and hours in a day because every time I shoot my rifle and it sends a tiny 30 round 30 30 caliber round or 22 like a 22 down the range, right? That's putting it down the range, but it's also putting it into my shoulder. So after a couple hours of shooting clay pigeons or putting rounds down a rifle range, my shoulder, I can feel it because it's shooting back. You got to be able to have a tight grip on these weapons because again of the forces that are at play there. So that's the whole idea behind um, Newton's three laws of motion. All right, working our way through the scientific revolution here. In terms of human anatomy, we have Andreas Vesalius. He's Flemish. Again, we talked about the area of Flanders, a little bit of Belgium, a little bit of northeastern France today. Now, Vesalius is a big deal in terms of human anatomy because he actually will go dissect human corpses. And he's going to prove the Roman kind of anatomist Galen wrong. Galen dissected dogs, and Galen dissected cats, and Galen dissected monkeys. And he gets a pretty good understanding of how those animals and their systems work, much like how human systems work. But a human is not a monkey, a human is not a dog. And so what Vesalius does by actually going dissecting human corpses, and why nobody's done this is because of the taboo of going and cutting up corpses and all this other stuff, not only in Roman times, but through medieval times, you can actually go and see how to do it. One of the key critical flaws of even modern medicine is that human beings cannot see into the human body. Now we have MRIs and CAT scans and PET scans and other ways of doing it today, which why makes medicine a lot more advanced. But I can't go if you say, Mr. Cranmer, I don't feel good, can I go to the nurse? I can't look at you and see what's causing you not to feel that way. I don't know if it's because you ate five different bags of gummy bears at lunch or you've got extra bacteria in your guts. I don't know that. And so Vesalius, by dissecting the human corpses and looking inside of that, is able to give a much more clear understanding of how human anatomy works. He's going to write this and draw diagrams in his book in 1543 on the structure of the human body. William Harvey is another English scientist, and he is the one that theorizes and proves that blood circulates throughout your body. That blood is not just stagnant and pooling, that your heart is pumping your body, your blood through your body, and that's how it's going and working. Robert Hooke is an English scientist, and he's going to use the microscope. And microscopes and lens technology has been developed by Antoine van Leeuwenhoek and the Dutch. And by looking at the microscope, Hooke is going to discover probably in quotation marks there, the cell and how there's building blocks that make up not only individual matter, and then people are going to ask, well, what makes up cells? And we can keep diving deeper and deeper into there. Edward Jenner is another famous scientist from England, and what Edward Jenner is going to prove is an idea of vaccination to be able to prevent smallpox. We talked about how terrible and horrible and awful the disease of smallpox was, and through Edward Jenner's experiments to prove that you can go and intentionally give people the disease cowpox, which you feel kind of wonky and not great for a couple of days, but you're gonna go and survive and not have to deal with that cowpox, nor smallpox, the greatest human killer of all time, of human history. That's a big deal. And that's why, of these guys, Edward Jenner probably has the largest effect on our lives today through proving that vaccination is a simple, easy, and effective way to prevent terrible, horrible disease from killing you or your babies. The Roman and medieval kind of worldview is that your body has different humors that are all working together. And so you need to be able to keep these humors in balance in order to be able to kind of have a healthy body. And this should go and make sense, right? If you don't feel well, right, you're going to have a temperature. That means your blood is running too hot. So how would I go and cure that? I would go and cut you open to let some of that blood out to cool you off. So this is why barbers' poles have a white stripe on them, because medieval barbers would go and cut your hair, but they'd also go and do bloodletting for you if you weren't feeling well, and then be able to bandage you up and send you on your way. Right? If you've got a running nose, you've got a lot of phlegm, that's liquid stuff, it's all in there, so you want to get rid of it. So you got to go and heat yourself up to be able to dry yourself out that way. So by keeping those humors in balance, that's how it's going to keep a healthy person. This doesn't work. Why does George Washington die? He's literally bled to death because he has a cold, and they just keep cutting him, bleeding and bleeding and bleeding, and he doesn't have any blood left in his body. And we see that happen multiple times through many famous people throughout history, as well as innumerable um, regular people, the Mr. Cranmers of the world. So to combat this view, we have Andreas Vesalius, and again, he actually goes and dissects human corpses, and from that he's able to make diagrams like we see in this, where if we go and remove the skin, this is what your muscles look like underneath your body, and everybody underneath their skin looks like this. This is your body. It just, do you have more padding? Do you have more skin? Do you have other things, right, that separates everybody from looking like this underneath their skin? William Harvey theorizes that blood circulates. He does that through tourniquets and by poking and prodding to be able to go that blood is circulating throughout your body. Robert Hooke works with Dutch lens technology to work with microscopes. That's his drawing of a lice that lives in your hair. So that's a human hair that the lice is holding onto, and this is what would go in. This is why lice are creepy to have and drinking your blood on your body. Two portraits of Edward Jenner, and Edward Jenner is a big deal because of his vaccination. Now we see in the painting on the right and the painting on the left, cows in there, because Edward Jenner began to make observations that milkmaids in England did not suffer from smallpox. And people begin to, Edward Jenner began to make the observation that why? Why is this the case? Why do milkmaids not suffer from smallpox the same as the rest of the population? So he began to make further observations and discovered that a lot of these milkmaids had cowpox. Cowpox is the disease that cows get, where you get inflammation and pustules on a cow's udder, right? That's where the milkmaids are milking from. Any cuts, any things in the skin, now you get cowpox, so you get some pustules. But this cowpox goes away, very similar to how you might get chickenpox, and chickenpox goes away. But importantly, by giving somebody cowpox, that prevented them from ever getting cowpox again, and also smallpox, which is a big deal. So what Edward Jenner said, what happens if I purposely give somebody cowpox, have them get that and develop that rash, then when that rash goes away, I purposely give them smallpox, what's going to happen? So Edward Jenner found a young woman with cowpox, popped one of these pustules, got it all nice and goopy on a knife, went to a 12-year-old boy named James Pips, Pips, right? Made an incision, took all that cowpox pus, rubbed it all in there. What happened? He developed cowpox. Let that disease run its course, didn't felt growth for a couple days, bounced right back, he's happy and healthy. Then he found someone with a major outbreak of smallpox. Again, got all the juices and goop and pus from the smallpox on a knife, went back to James Pips, purposely gave him smallpox, and what happened? James Pips did not develop smallpox because he already had an immune response and antibodies in his body for both smallpox and cowpox. And so this is why we see women during this time being described with milky white skin, and everybody loving the idea of going out on a date with a milkmaid, because they're not all pockmarked and covered in smallpox marks like the rest of society is. This is a major advancement. This is a big deal. And this then further allows for further experimentation with other diseases so that people aren't dying from tetanus, right? Where your jaw literally locks up and where you have violent convulsions so much that you break your back because of bacteria and this virus getting into your body. You don't get whooping cough, where you have to watch your infant son or daughter cough themselves violently, pretty much to death. Measles, rubella, all these diseases that were the plague of humankind since pretty much the beginning of cities and agriculture now can be wiped away with a single healthy, safe shot that you'd be an idiot not to give your child. Like today, though, because we have a ton of idiots out there, right? People are misunderstanding how these vaccines work. But again, this is very similar to what the ancient Chinese, what the ancient Egyptians are doing to help prevent the spread of smallpox in their time periods. So we get people here, the French, the origin of the vaccine from the cows, and going making fun of it that. So again, if you give someone cowpox, what's going to happen? Well, if you this thing in France, right? What the English are doing is they're getting cows growing out of their nose or out of their armpits or out of their forearms. So you don't want a vaccine if you're in France, which again is a fool's errand and fool's thoughts. To finish up here, when we're talking about the scientific revolution getting into chemistry, Robert Boyle is an Irish chemist, and he's famous for coming up with what's called Boyle's Law. And we'll show you a GIF, and we'll show you, hopefully, if you went in class and saw the video I showed you in class about how gases react to temperature. Boyle is referred to as the father of modern chemistry. So when you take chemistry, usually as a sophomore in high school, he's kind of a big deal in describing how a lot of modern chemistry works and the foundational stuff for that. Joseph Priestley is an English chemist, and he helps discover the existence of oxygen. He helps work with the idea of laughing gas. Laughing gas is a gas that you can inhale, which is going to knock you out and act as an anesthetic to be able so that you're not going to be able to feel pain as someone is actively cutting open your mouth or your body, which is a good thing. And you're going to feel it afterwards, right? But you're not going to feel it during, which is very helpful for conducting surgeries. Joseph Priestley also helps describe carbonated beverages that exist in nature, as well as creating carbonated beverages by hand, by mankind, say through how sparkling wine or champagne is made. The Lavoisiers, Antoine and Marie Lavoisier, are French, and they are chemists who helped discover that combustion, fire, very much revolves around the idea of oxygen being consumed by that fire. So if you remove oxygen or lessen the oxygen that a fire gets, you're going to slow and or stop that fire from going. If you go to a fancy restaurant on a date in high school and there's a candle between, you can go and put something hopefully flame proof, fireproof over that candle, right? And you eventually will go and see that that candle will start to dim and then go out because there's no more oxygen for that flame to go and get. Why you're told to stop, drop, and roll if you catch on fire is you're trying to be able to lessen the amount of oxygen that that fire is getting. Right? If you start running, you're gonna get the wind and the flames. You're gonna make it worse. Our last of our chemists is going to be Humphrey Davy, and he's working in the early 1800s dealing with miners. And what he begins to discover is that when these coal miners, particularly in Wales and in England, are going down into the ground and pulling out this coal, what is also trapped under the ground are large deposits of methane gas. Methane gas is flammable. And so what happens is that these guys who are going down in these dark um, mines are bringing with them candles to see flame and methane gas causes kaboom explosions. So what he devises is what's called the safety lamp for miners, which basically allows England to have an industrial revolution because miners can now safely work. Davy discovered that oxygen molecules are small, so they can fit through very fine mesh to be able to get to a candle and light it to provide light. Methane molecules are relatively large, so they cannot fit through this very fine mesh that he devises, so the methane stays out, the oxygen goes through, so you can see in the mines. Might not be best for breathing, but you can at least see and you lessen the risk of explosions. So to finish up this longer video that we have, Charles Boyle, again, is famous for Boyle's Law, which describes when you decrease the volume of a gas, you're going to increase the pressure. If you decrease the volume of a gas, you're going to decrease the pressure. You can see this in terms of temperature as well. When you go and you decrease the volume, you're going to actually increase the temperature. And verifying to get this in. And again, you can see this with a balloon when you're going and blowing up a balloon there. Joseph Priestley again works with oxygen in carbonated beverages. The Lavoisiers deal with oxygen consumption, working with combustion and fire. And Humphrey Davy, and with that's a very fancy and very fitting end here, works with his safety lamp for miners, which he goes and develops, which again basically allows the Industrial Revolution to exist in England and thus around the world. So longer lecture when we had to get into a little bit of the introduction, and then we wanted to make sure we understood the scientific revolution. So we're going to end that discussion on the scientific revolution of the Enlightenment, and in our next video on the Enlightenment, work in how philosophy begins to change during this time period in Europe.